Gravitational waves are ripples in the fabric of space-time, generated by massive cosmic events such as colliding black holes or neutron stars. These waves travel across the universe, carrying information about their origins and the nature of gravity itself. Studying gravitational waves has opened a new window into the cosmos, allowing scientists to observe phenomena that were previously invisible using traditional telescopes. Their detection has confirmed key predictions of Einstein's theory of general relativity and provided insights into the behavior of matter under extreme conditions. In modern cosmology, gravitational wave research is crucial for understanding the evolution of the universe, probing the mysteries of dark matter and dark energy, and exploring the fundamental laws that govern our reality. Gravitational waves are ripples in the fabric of space-time, caused by massive objects accelerating through space. These waves were first predicted by Albert Einstein in 1916 as a consequence of his general theory of relativity. According to Einstein, gravity is not simply a force between masses, but a result of the curvature of space-time itself. When massive bodies such as black holes or neutron stars move or collide, they create disturbances that propagate outward at the speed of light. These gravitational waves carry information about their origins and about the nature of gravity. For decades, they remained a theoretical concept, as their effects are extremely subtle and difficult to detect. Only in recent years have scientists developed instruments sensitive enough to observe these elusive waves directly. Gravitational waves originate from some of the most dramatic events in the universe. When massive objects like black holes or neutron stars collide, they create powerful ripples in the fabric of space-time. These waves travel outward from the source, carrying information about the nature of the collision and the objects involved. Such cosmic events are rare but immensely energetic, making the resulting gravitational waves detectable across vast distances. By studying these waves, scientists gain valuable insights into the universe's most mysterious phenomena. Gravitational waves are ripples in the fabric of space-time, created by massive cosmic events such as colliding black holes or neutron stars. As these waves travel across the universe, they stretch and compress space itself, carrying energy away from their sources. Although their effects are incredibly subtle, gravitational waves can influence the arrangement and movement of galaxies over vast timescales. By observing these waves, scientists gain valuable insights into the origins and evolution of cosmic structures. This ongoing research helps us understand how the universe has changed since its earliest moments, revealing connections between gravity, matter, and the large-scale architecture of space. Detecting gravitational waves presents significant challenges due to their incredibly faint signals. These waves, which are ripples in the fabric of space-time, are generated by massive cosmic events such as merging black holes or neutron stars. However, by the time they reach Earth, their effects are minuscule, often distorting distances by less than a fraction of the width of an atomic nucleus. This makes them extremely difficult to observe, requiring highly sensitive instruments and advanced technology. Environmental noise, such as seismic activity or human-made vibrations, can easily mask these subtle signals. As a result, scientists must carefully isolate and filter data to distinguish genuine gravitational waves from background interference. The complexity of these observations highlights both the ingenuity and persistence required in modern astrophysics. Modern gravitational wave detectors, such as LIGO and Virgo, utilize highly sensitive laser interferometry to observe minuscule distortions in space-time caused by passing gravitational waves. These facilities consist of long, perpendicular arms equipped with mirrors at each end. When a gravitational wave passes through Earth, it slightly alters the length of these arms, changing the pattern of laser light reflected between the mirrors. By measuring these tiny changes, scientists can detect and analyze gravitational waves originating from cosmic events like colliding black holes or neutron stars. The technology requires extreme precision, as the distortions measured are often smaller than a fraction of the width of a proton. Continuous upgrades and improvements in sensitivity allow these observatories to capture more distant and subtle events, expanding our understanding of the universe. In 2015, scientists made a groundbreaking discovery by detecting gravitational waves for the first time. These ripples in the fabric of space-time were predicted by Albert Einstein a century earlier, but had never been observed until then. The detection was achieved using highly sensitive instruments that measured tiny distortions caused by the collision of two massive black holes. This historic moment confirmed a key aspect of Einstein's theory of general relativity and opened a new window for exploring the universe. Gravitational waves allow researchers to study cosmic events that are invisible to traditional telescopes, deepening our understanding of the origins and structure of the cosmos. The discovery has since inspired further advancements in astrophysics and technology, marking a new era in scientific exploration. Gravitational wave data analysis is a fascinating process that allows scientists to listen to cosmic collisions. When massive objects like black holes or neutron stars merge, they create ripples in the fabric of space-time, known as gravitational waves. Specialized detectors, such as LIGO and Virgo, capture these faint signals as they pass through Earth. Researchers then use advanced algorithms to filter out background noise and isolate the unique patterns produced by these events. By studying the frequency, amplitude, and duration of the waves, scientists can determine the properties of the colliding objects. This method provides valuable insights into phenomena that are otherwise invisible, deepening our understanding of the universe. Recent research into gravitational waves has led to several remarkable discoveries. Scientists have observed the collision of black holes, events that release immense energy and cause ripples through the fabric of space-time. Additionally, the merging of neutron stars has provided valuable insights into the origins of heavy elements in the universe. These observations have confirmed key predictions of Einstein's theory of general relativity. By detecting and analyzing these cosmic events, researchers are gaining a deeper understanding of the universe's most extreme phenomena. Each new finding continues to expand our knowledge of how matter and energy interact on a grand scale. Gravitational waves have revolutionized our understanding of the universe's origins and evolution. By detecting these ripples in space-time, scientists can observe events that were previously hidden, such as the collision of black holes and neutron stars. These observations provide direct evidence of phenomena predicted by Einstein's theory of general relativity. Gravitational waves also offer insights into the earliest moments after the Big Bang, helping researchers piece together the universe's history. As technology advances, the study of gravitational waves continues to reveal new information about cosmic processes, deepening our knowledge of how the universe has changed over time. Gravitational wave technology has opened new avenues in both physics and astronomy. By detecting these waves, scientists can observe cosmic events that were previously inaccessible, such as black hole mergers and neutron star collisions. This technology also enhances our understanding of the fundamental forces of nature and the structure of space-time. In astronomy, gravitational wave observations complement traditional methods, providing deeper insights into the origins and evolution of the universe. Additionally, research in this field drives innovation in sensor technology and data analysis, which can be applied to other scientific disciplines. The ongoing development of gravitational wave detectors continues to expand our ability to explore and understand the cosmos. Despite remarkable progress in gravitational wave research, several questions remain unanswered. Scientists are still investigating the precise origins of certain detected signals and the full range of astrophysical phenomena that can produce gravitational waves. The nature of black holes and neutron star mergers continues to be a subject of intense study, as does the possibility of detecting waves from the early universe. Looking ahead, advancements in detector sensitivity and global collaboration promise to reveal new insights. Future research may uncover previously unknown sources and help refine our understanding of fundamental physics. The field remains dynamic, with each discovery opening new avenues for exploration. Gravitational waves have revolutionized our understanding of the universe. By detecting these subtle ripples in space-time, scientists can observe cosmic events that were previously hidden, such as the collision of black holes and neutron stars. This new window into the cosmos has not only confirmed key predictions of Einstein's theory of relativity, but also revealed phenomena that challenge existing models. The study of gravitational waves continues to inspire technological innovation and international collaboration. As research advances, these discoveries promise to deepen our knowledge of the universe and spark new questions about its origins and evolution.